All right, so we're going to start talking about acids and bases. And so some of the things you might be already familiar of are the fact that we have the pH scale, which is kind of shown here. You might be familiar with the fact that things like lemon juice, battery acid are pretty acidic. Um, Drain cleaner, things like that, baking soda are basic. We're going to talk a little bit in more detail about the chemistry, why this happens. So the first thing we need to understand is that water goes through what's called self-ionization. And what that simply means is that when two water molecules collide, they actually transfer a hydrogen from one to the other. So when you have a collision between water molecules in a sample of water, one of these little white hydrogens is going to potentially be transferred over to the other water molecule, and it's not taking its electron with it. And it's just the proton, it's just the hydrogen nucleus. And that's why the water molecule that gets that proton becomes H3O with a +1 charge because it didn't get the electron, it just got the positive proton. And then the water molecule that lost that proton is going to be OH1 minus because it kept the electron but lost the positive proton. So that's the self-ionization of water. This is happening in any sample of water. So there's a certain amount of this guy on the left, which is called hydronium. It's a polyatomic ion. And this guy on the right, which you already know is hydroxide, in any sample of water. Okay, it's a small amount, but there is some there. So what is it that makes something an acid? According to Arrhenius, an acid was anything that increases hydronium concentration. So this was the first molecular level explanation of what makes an acid an acid. And so, for example, if you were to look at the reaction of hydrochloric acid, HCl, this is the stuff that's in your stomach acid. Hydrochloric acid, when it comes into contact with water, it is going to increase hydronium. And the way that it does that is it gives its hydrogen to the water molecule, again, making hydronium just like what happened up here. Only here, notice it's a one-way arrow, which means it's going to make a lot more hydronium than you get from simply two water molecules colliding. It also leaves behind the chloride because, of course, that would be what you would get if you had HCl and you took away an H+. Another example would be sulfuric acid. So this is what's in battery acid, like a lead acid battery in a car. H2SO4 plus water. So again, a hydrogen from here is going to get transferred to the water. It's going to make hydronium. Now, one thing I want you to notice here is even though there were two hydrogens in sulfuric acid, they don't both get transferred, at least not initially. We'll talk about the possibility of this second hydrogen being added to water a little bit later on, but it's just going to be one hydronium that gets made. Now, both of these are referred to as acid ionization reactions or acid ionization equations because, of course, we're forming positive and negative ions. Now, bases, on the other hand, according to Arrhenius, again, is anything that increases hydroxide, so just the opposite. So in pure water, we have hydronium and hydroxide, and we have them in equal amounts. And we have them in small amounts, very, very low concentrations. But acids are going to cause the hydronium to jump way up. Bases are going to cause the hydroxide to jump way up. Now, the way that a base does that, so for example, LiOH is an example of a base. It's going to do this by dissolving. So rather than changing a water molecule, it's simply going to get pulled apart, just like any other ionic compound as it dissolves in water. So it's going to get pulled apart, and so for that reason, we put the water above the arrow, just like we would in any dissolving process, and we get the two ions, Li plus and OH minus. And so it's the presence of that hydroxide that tells us that this thing is going to be basic. Another example, aluminum hydroxide. Again, it ends in hydroxide, so you would anticipate that if you dissolve it in water, which you can, it's going to break up and it's going to form Al3 plus and it's going to form 3 OH minuses. Now notice, unlike with H2SO4, where we said only one hydronium gets made because only one hydrogen gets donated, a base ionization is just dissolving. So it is actually going to produce however many hydroxides were in the original base. So if aluminum hydroxide has 3 hydroxides, you're going to have a coefficient of 3 on the OHs on the right side. All right, so let's talk a little bit about acid-base properties. So acids are generally characterized by number one, their taste. So it's not, of course, recommended in the lab that you taste an acid, but you've probably tasted plenty of acids before, like citrus fruit, right? It's very sour, and that's because it has ascorbic acid, which is vitamin C, citric acid, all kinds of stuff in those lemons and limes and grapefruits and oranges and things. They conduct electricity, and that's because they have ions, right? Hydronium for one, definitely. And they should also have a negative ion in there as well, so they can conduct electricity. Okay. Another one is they react with active metals. So if you remember our single replacement reactions, our activity series, active means they're higher up on the list. So for example, if we have hydrochloric acid, and by the way, I can guess that this is an acid even if I don't know this is hydrochloric acid, because generally speaking, acids are going to start with H out in front. They're going to have that hydrogen, and that H is what's going to actually be, you know, moving, getting taken off of the acid. And in this case, the magnesium takes the H off the acid in a single replacement reaction, but one of the products is going to be hydrogen gas. So like in this little picture here, a little piece of magnesium ribbon has been dropped into a liquid. That liquid happens to be hydrochloric acid. You see all the bubbles being given off. That's hydrogen gas. So if you were to light a match and hold it over that test tube, you would get a little pop or a small explosion as that hydrogen ignites. And that would tell you that the liquid must have been acidic. And then the last one is, you know that an acid is an acid when it neutralizes a base. So acids and bases neutralize each other. We're going to talk about that more a little bit later on. Okay, so what are base properties? Well, if acids taste sour, bases taste bitter. Okay, so for example, a poppy plant. Let me move myself out of the way here. If you were a hunter-gatherer, you know, collecting seeds and fruits and things like that to eat, one of these things is going to taste pretty awful. It's also going to give you, you know, it's going to have a psychoactive effect because it's a drug. But essentially, the reason that it tastes bitter is because, and also the reason that it's a drug is because um, it has plant evolved toxins that are that have evolved to kill or at least dissuade anything from trying to eat it. And so the same thing is true of like nicotine in a tobacco plant or THC in a marijuana plant. Those are plant-derived toxins that happen to be basic in nature, and that's why they taste bitter. Um, they conduct electricity. They also have positive and negative ions. They feel slippery. We don't want to be feeling things like sodium hydroxide, which is a strong base, but you know, soap is basic and it does in fact feel slippery. Also, if you've ever had your mouth washed out with soap, I don't think that's a very, very common practice anymore, but it used to be if you used a bad word when you were a little kid, you got, you know, a bar of soap stuck in your mouth or whatever, and it tastes bitter. That's because soap is basic. It's also slippery, which is a characteristic of a base. And just like acids neutralize bases, of course, bases neutralize acids. Okay, last thing we need to talk about is what do we do about naming these things? Bases are easy. Bases, we just use the same system we've always used because they just end in hydroxide. Lithium hydroxide, sodium hydroxide, calcium hydroxide. Acids have a different system though, okay? So for example, when we see HCl is hydrochloric acid, H2SO4 is sulfuric acid, HClO2 is chlorous acid. How did they get those names? Why do some of them start with hydro and some of them not? Why do some of them end with ic and some of them end with us? And here's the system. The first rule is if the negative ion ends in, if the negative ion ends in ide, IDE, the acid is going to start with hydro and end with ic. So for example, up here we have chloride, right? And so this is going, so HCl is going to be considered hydrochloric acid, okay? Oops, there we go. If we have, you know, anything that ends in I, so chloride as an acid is hydrochloric acid. So it starts with hydro, ends with ic. All right, and then the next rule is if the anion or negative ion ends in 8. So for example, the second one up here, H2SO4, that negative ion, SO4 2- is called sulfate, right? So there, the anion ends in 8. So we don't give it a hydro prefix, right? We just give it an ic suffix. So this becomes sulfuric acid. So sulfate becomes sulfuric acid, okay? Then the last rule is if the anion ends in ite, the acid gets no prefix and then it gets an us ending, okay? So this last example up here, HClO2, you might recognize ClO2 1- is chlorite. Okay, so if the anion ends in ite, we're going to make the acid end in us. So it's going to be chlorus acid. Okay, all right. Try these 4 examples. Maybe pause and give them a shot and see if you can apply the rules, and then I'll go over them. Okay, so this first one should be carbonic acid. Okay, so the negative ion is carbonate, and so the rule is if the anion ends in ate, no prefix, and we just give it an ic suffix. So carbonate becomes carbonic acid. Right? HF, the negative ion here is fluoride, just fluorine from the periodic table, F-. And so we go with the first rule. If the anion ends in ide, hydro prefix, ic suffix, and then the word acid. So hydrofluoric acid. And then the next one, N, here with a 3- charge, once again, is just nitride from the periodic table. So again, it goes with our first rule. Nitride ends in ide, so this is going to be hydronitric acid. And then the last one, looks like we have phosphate. I think I meant to give you phosphite there, but it did give you phosphate, so it would be our second rule, which would be phosphoric acid. Okay, and that's our rule for naming acids. Bases, again, we don't really need rules because they're just going to be lithium hydroxide, aluminum hydroxide, and so forth. All right, guys, and we'll go through more practice in class.